Hello there, welcome to Fundamentals of Biology, Lesson 2, which is on chemical bonds. This lesson should really be Lesson 1B, as it follows on from the previous one where we looked at elements and atomic structure. And in this session, we're going to have a look at taking those atoms that we looked at previously, and we're going to join them together to make chemical bonds. So in this section, we're going to talk about two particular types of bonds that we come across frequently in biology, and they are ionic bonds and covalent bonds. And I'm going to finish this off just by talking to you a little bit about the difference between polar and non-polar covalent bonds. They have quite a big and important difference. So just a quick recap on what we discussed previously then. And as I stated, as I pointed out, we don't see, when we look around us, as just a random soup of atoms. We see complexity and order in the universe around us. And that is because atoms can come together to complete their valence shells. So if you remember, valence shells are the outermost shell, and the electrons in those valence shells, so the valence electrons, are what determine the chemical behavior of an atom. And by chemical behavior, I mean how those atoms interact with each other to make compounds and molecules. So today we're going to look at how those compounds and molecules are formed. So again, just a quick recap. A compound is a substance consisting of two or more different elements in a fixed ratio. So the important thing here is that a compound is made up of two or more different elements. So we can see them down in the bottom left-hand corner there. So a classic example would be water, made up of oxygen and hydrogen, and carbon dioxide, which is made up of carbon and oxygen in a fixed ratio of 2:1, 2 oxygens to 1 carbon. So we get the two different elements, and we get the fixed ratio also. And again, just to recap, a compound will often have different characteristics from those of its elements. So the example that is often used is sodium chloride. So you take the metal sodium and the gas chlorine, combine them in the fixed ratio of 1:1, and you get sodium chloride or normal table salt. Okay, so that's compounds then. A molecule is a substance consisting of two or more atoms joined by chemical bonds. So molecules can consist of two or more atoms of the same element. So classic examples in the bottom right-hand corner, we get molecular hydrogen, oxygen, nitrogen, and chlorine. And we can see that each one is just two atoms of the same element joined together. So here's that example that I just went over, and I did in the previous video as well. Sodium chloride, a fixed ratio of 1:1, 1 atom of sodium, 1 atom of chlorine gives you sodium chloride. And we're going to have a look at that as an example in a minute of how those two atoms are actually joined together to make an ionic bond. Okay then, so again, this is a further recap from the previous video. So the formation of molecules and compounds depend on chemical bonding between atoms, and atoms with incomplete valence shells can share or transfer valence electrons with certain other atoms. And when this happens, the interactions result in atoms staying close together, held by attractions called chemical bonds. So, as I previously stated, the two main types of chemical bonds that we encounter are ionic and covalent bonds. There are several others that we'll look at as we go through subsequent lessons, but ionic and covalent are the two main ones. So those are the ones that we're going to focus on today. So let's start by looking at ionic bonds then. So an ionic bond is a chemical bond in which one atom gives up an electron to another. And this creates a bond formed by the attraction between two oppositely charged ions. So to understand what this means, we first need to understand what ions are really. So typically standing, when we have an atom, as we discussed previously, we can tell the number of protons that an atom has by looking at its atomic number. So looking at the example on the PowerPoint here, we can see that we have sodium, and we know that sodium has, if you look at the periodic table, we can see that sodium has an atomic number of 11. So that tells us it has 11 protons, and it also has 11 electrons. And if you also remember that protons are positively charged and electrons are negatively charged, we can see that they balance each other out. There's 11 positives and 11 negatives. So overall, that atom is neutral. The positives and the negatives balance each other out. And if we look to the right, we can see chlorine. It has an atomic number of 17. So 17 protons, 17 electrons. The positives and the negatives balance each other out. And this is the typical state of any given atom. They are electrically neutral because they balance each other out. Same number of protons as electrons. But what can happen, and as we'll see in a minute, is these atoms can gain or lose electrons. And when that happens, you end up with an unbalanced atom in the sense that they may have gained an extra electron or they may have lost an electron. If an atom gains an extra electron, because it's gaining an extra electron, that's an extra unit of negative charge, that atom is now negatively charged, and we would say that that is now called an ion because it has an electrical charge. Similarly, if an atom loses an electron, because it has lost a unit of negative charge, it will now have one extra proton in its nucleus than it does electrons around the nucleus. So it is now a positively charged ion. And we can actually give these actually have specific names. So if an atom loses an electron and becomes a positive ion, they are called cations. And if an atom gains an electron and becomes a negatively charged ion, that is called an anion. Now, there is an easy way to remember this, but it's not something that I'm particularly proud of. It's a bit childish, but I'll share it with you anyway because it can help to remember these things. So if you get confused over which ones are cations and which ones are anions, easy way to remember it is cats have pores. So pores positive, so cations are positive, and that leaves anions as negatives. Like I said, I'm not proud of that one, but it works. So I've got a little animation here. So we'll watch what happens when an atom of sodium encounters an atom of chlorine, and what we'll see here is the formation of two ions. So if you keep an eye out, you'll see that sodium will become a cation. So sodium is actually going to lose this extra or this spare electron out here, this one single valence electron. It's going to lose that. That electron is going to move over here, and it's going to join the valence shell of chlorine. So that means that sodium loses an electron. So it will then have 11 protons, but only 10 electrons. So sodium is going to become a cation. Chlorine is going to gain an extra electron. So it will have 17 protons, but 18 electrons. So chlorine will become an anion. And what happens with that then is because you've got a positive ion and a negative ion, they will be attracted to each other. Positives and negatives attract. And the attraction between the positive and the negative anion, between the positive and negative ions, will keep them in close proximity with each other. And that closeness is what we refer to as an ionic bond. They'll stay together because of that attraction. So let's watch this, and then I'll come back to it afterwards.
Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons, but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion, in this case, a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
Okay.
Sometimes
So here's just a diagram showing the same thing that little animation showed. So here we've got an atom of sodium, and we can see its electron configuration written here. It's 11 electrons, 2 go in the first shell, 8 in the second, and then 1 in the third. And here we can see the electron configuration written for chlorine. So its atomic number is 17. So 17 electrons, 2 in the first shell, 8 in the second shell, and then that leaves 7 in the third shell. Important thing to remember, as we covered in the previous video, is that all atoms want to have a complete valence shell. So when sodium and chlorine come into close proximity, this spare, or this lone electron in the valence shell of sodium will move over to chlorine like this, and then that leaves us with sodium now becoming a cation. It is now a positive ion, and then chlorine is a negative ion. It is an anion, and then we get the attraction between the positive and the negative, and that attraction holds them together, and that is what we refer to as an ionic bond. And ionic bonds typically form between a metal and a non-metal, and they will often form salts. Okay, so moving on to covalent bonds then, we see that a covalent bond is a chemical bond formed by the sharing of one or more electrons, especially pairs of electrons, between atoms. So whereas ionic bonds are created when one atom gives up an electron and one gains it, so you get this actual transfer of electrons, covalent bonds are formed by the sharing of electrons between atoms. And as we'll see when we go through, different atoms can share 1 electron each, or in some cases they'll share 2 electrons each. And rarely, but we do see it, they can share 3 electrons each, so 3 pairs of electrons. And as we go through, we'll look at the different ways in which we can write this down as well. So I've got a little animation here again, so we'll watch this, and then we'll go on and we'll talk more about covalent bonds.
A covalent bond is the sharing of a pair of outer shell electrons by 2 atoms. For example, each of these hydrogen atoms has 1 electron in its outer shell, but needs 2 electrons to complete its outer shell. If the 2 hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as 2 or more atoms held together by covalent bonds. An oxygen atom needs 2 electrons to complete its outer shell. 2 oxygen atoms can share 2 pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, 2 shared pairs of electrons. A carbon atom needs 4 electrons to complete its outer shell. It can share electrons with 4 hydrogen atoms, forming a methane molecule containing 4 single covalent bonds. Methane is a compound, a substance formed by the combination of 2 or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs 2 additional electrons to fill its outer shell. Thus it can form 2 single covalent bonds. An oxygen atom can share electrons with 2 hydrogen atoms, forming a molecule of water containing 2 single covalent bonds.
Okay, so there we can see a few different examples of covalent bonds. So let's go through and we can talk about some of them in a bit more detail. So Here we can see two atoms of hydrogen coming together. Obviously, each hydrogen just has one electron in its first shell, but it wants two. So the two hydrogen atoms can come into close proximity and they can actually share those two electrons, so one each. And that means now that each atom is associated with two electrons, which means essentially that their valence shell is complete. So they are happy. The way that we would write this down is quite simply like this. We can see two hydrogens joined by one line. That one line isn't irrelevant. That one single line tells us that these two hydrogen atoms are joined by a single covalent bond. And a single covalent bond is the sharing of just one pair of electrons. So each atom is donating just one electron to the bond. And as we see as we go through, this can sometimes be 2 or 3 lines. Okay, so here's another example that was just on the animation, and it's water. So 2 hydrogens plus an oxygen. So we can see the 2 hydrogens here, each with their lone valence electron. Here we've got oxygen. We know that oxygen has an atomic number of 8. So 2 electrons go in its first shell, and then you can see the valence shell here with its 6 electrons. So oxygen wants 2 additional electrons, and it can get those by sharing 2 of its electrons with hydrogens. So here we can see a covalent bond between the hydrogen and the oxygen, and a covalent bond between the oxygen and the hydrogen here. And because we've got 2 single covalent bonds again, we can draw it like this, or write it down like this. 1 oxygen, 2 hydrogens, each hydrogen joined to the oxygen with one line which shows or represents a single covalent bond. Also on the video, or on the animation there, we saw methane. And methane is probably the simplest of our hydrocarbons. So we start off with a carbon atom here. So we know that carbon has an atomic number of 6. So it has 6 electrons, 2 in the first shell, and then 4 valence electrons. And we discussed this in the previous video. This is why carbon is believed to be the main element that life is built around, because it can make 4 bonds with other atoms. In this instance, this carbon atom can join to these 4 hydrogens, and it will look like this. So there's the carbon. It is sharing its 4 valence electrons with 4 atoms of hydrogen, which each of those atoms of hydrogen share their single valence electron with the carbon. So carbon is now associated with 2, 4, 6, 8 valence electrons. So carbon is happy. Each hydrogen is associated with 2 valence electrons. So they are all happy. And that gives us CH4, which is a molecule of methane. And we can, again, draw it or write it down like this. Carbon with 4 single lines to 4 hydrogens. Each line shows us that there is a single covalent bond there, the sharing of one pair of electrons. Okay, when we look at carbon dioxide, we can see something a little different. We can see the formation of double covalent bonds. So here's carbon again with its 6 electrons, so 4 valence electrons, and 2 oxygens, each oxygen with its 6 valence electrons needing to get hold of 2 more. So we've got an oxygen here and an oxygen here. And then we can see that the carbon will actually donate 2 of its electrons, and each oxygen will donate 2 of its electrons. So we actually get the formation of 2 double covalent bonds. And you can see that down here represented by 2 lines. And that tells us that we get the sharing of 2 pairs of electrons between the carbon and each of its oxygens. Okay, so that's what we refer to as double covalent bonds. In rare cases, we can get triple covalent bonds. And we don't come across them, or we won't talk about them very often at all. But just so you're aware, here is an example of one. So again, we know that carbon wants to make 4 bonds. So here's carbon. It can make a bond with hydrogen over here, and that leaves it 3 bonds to make. And it can actually share 3 of its valence electrons with a nitrogen atom. And nitrogen wants 3 additional electrons to complete its valence shell, so it will share 3 of its electrons with carbon, and that will actually form a triple covalent bond. And that's shown by those 3 straight lines. And you can see it up here where you've got the sharing of 3 pairs of electrons. So there we can see covalent bonds, the sharing of electrons. Typically, we'll see single covalent bonds, but we will look at in the next session some examples of double covalent bonds. They are quite important in forming biological molecules. And in rare cases, we can also get these triple covalent bonds, like in hydrogen cyanide. So just to finish off this section then, I wanted to talk to you a little bit about something called polar and non-polar covalent bonds. So we just talked about covalent bonds, so the sharing of electrons. But covalent bonds do come in 2 main types, polar and non-polar. So and they do make a big difference to how the molecules and compounds that they create behave. So let's go through and we'll talk a little bit about them. So first, let's look at polar covalent bonds. And a polar covalent bond is formed when a shared pair of electrons are not shared equally. So what I mean by that is, if we take this diagram down here, and let's use a classic example that we've looked at already with water. So if we can think that atom B here is the oxygen atom making up a water molecule, and atom A is one of the hydrogen atoms. Okay, so we've got oxygen as atom B, and then we've got one of the hydrogens as atom A. If these 2 red dots here, or these 2 red balls, are the shared electrons, so the shared pair of electrons making a covalent bond between the oxygen and one of its hydrogens, what we can actually see is that these electrons don't just sit nicely equidistant between the 2 atoms. Instead, they're moving closer towards the oxygen atom, and that is because of something called electronegativity. So oxygen is a highly electronegative atom. What that means is, in covalent bonds, it exerts a very strong pull on the shared electrons that make up the covalent bond. And different atoms will have different levels of electronegativity. So fluorine is the most electronegative atom, but oxygen is also incredibly electronegative, so it exerts a very strong pull. In fact, oxygen is much more electronegative than hydrogen. So when you get a covalent bond between oxygen and hydrogen, the shared electrons sit much closer to the oxygen atom than they do the hydrogen. Now, you might wonder why that's important, but it goes back to something that we've talked about quite a bit already. It's about the electrons and about the electrical charges involved. So we know that electrons are negatively charged. So if you've got 2 negatively charged electrons here, and they are sitting really close to this oxygen atom, it is almost gained 2 extra electrons. So you could say that it's gained 2 extra units of negative charge. That will mean that this part of the water molecule, the part of the water molecule where the oxygen is, will be negatively charged, or will carry a slight negative charge, because it is holding on to those electrons of the covalent bond. Poor old hydrogen over here, it's kind of losing its grip on its own electron and the shared one it's getting from oxygen. It's moving away from the nucleus of the hydrogen. So its nucleus, which with hydrogen is just that lone proton, is kind of exposed over here. And we know that protons are positively charged. So the hydrogen side, or the hydrogen parts of a water molecule, will actually carry a slight positive charge because you've got those positively charged protons sort of exposed because they've lost their grip on their electrons. So a polar covalent bond then is due to one of the elements having a higher electronegativity than the other. And if you are particularly interested in chemistry, you can go online and you can search for something called an electronegativity table, and it will bring up all of the different the different levels of electronegativity for the atoms, for the elements. So electronegativity then is a measure of the tendency of an atom to attract a bonding pair of electrons. So we'll also see this in later lessons as well, when we see covalent bonds between nitrogen and hydrogen. Nitrogen, a bit like oxygen, is more electronegative than hydrogen. So in those covalent bonds, the electrons will sit much closer to nitrogen than they do hydrogen. So what does this mean for water then, as that's the example that I just used? Well, the shared electrons between oxygen and hydrogen in a water molecule are not shared equally because oxygen is much more electronegative than hydrogen, which is what we just discussed. This creates something called polarity. And polarity is where the water molecule has a partial positive charge on the hydrogens and a partial negative charge on the oxygen. So we can see that over here on this diagram. So here's the oxygen part of the molecule, and it has a slight negative charge. And then here are the two hydrogens, and you can see that they have slight positive charges. So why is that important? Why does it matter? Well, this polarity, this positive and negative components of the same molecule enables water molecules to form bonds with each other, specifically hydrogen bonds. And what this enables them to do is water molecules can sort of join together through these hydrogen bonds, but also it enables water to dissolve other substances that are polar, so other substances that have both positive and negative parts to them. And that's what makes water such an important solvent. So a solvent is something that can dissolve other substances. Water is an incredibly versatile solvent because of its polarity. And with this little diagram here, we can see how the water molecules will form hydrogen bonds between each other. So if we take this top left-hand one here, we've got the negatively charged oxygen with the positively charged hydrogens. Well, when you add more water molecules, you'll see hydrogen bonds denoted by these dotted lines here forming between the positively charged hydrogens and the negatively charged oxygens. And these can actually, although individually they're very weak bonds, when you get lots of them together, they can be surprisingly tough. So if you've ever experienced surface tension, so if you've ever done a belly flop whilst diving into water or jumping into water, that impact that you get on the water is created by the resistance of these hydrogen bonds. Similarly, if you've ever filled a glass up slowly, if you fill a glass up slowly, what you'll notice is the water level will actually rise above the top of the glass. You'll get a bulge at the top of the glass, and that again is being held together by these hydrogen bonds between the water molecules. Eventually, if you keep filling the glass, you will overcome these hydrogen bonds, and they will start to break. You'll break the surface tension, and the water will start to flow over the sides of the glass. Okay, so we'll talk more about water in a later session because it's so important. So those are polar covalent bonds, but we also get non-polar covalent bonds, and hopefully you've figured out what they mean now, or what they are. But just to cover it quickly, a non-polar covalent bond is a bond that is formed when electrons are shared equally between two atoms. So this occurs between atoms with similar levels of electronegativity. So the classic example is what we can see on the board, on the PowerPoint here, and it's one that we've discussed already, and it's methane, Ch4. the levels of electronegativity are very similar between carbon and hydrogen. So when they form these covalent bonds, so if you remember, methane has 4 covalent bonds, 4 single covalent bonds between the carbon and 4 hydrogens. Well, because they have similar levels of electronegativity, the shared electrons actually sit fairly equally or evenly between the 2 nuclei. So that makes a non-polar covalent bond. That means that there is no electrical charge around them, so they are less likely to form bonds with other atoms. They're much less likely to form hydrogen bonds with water, things like that. Okay, so those are polar and non-polar covalent bonds. We'll come and we'll talk more about those in later lessons. So now we've had a look at atoms and elements and atomic structure, and we've joined some atoms together to form compounds and molecules using ionic and covalent bonds. That kind of brings us towards the end of this first session. So just to finish off then and prepare you for the coming few sessions, we can now start talking about something called organic chemistry. And this is the study of compounds that contain carbon. And organic compounds are really diverse. They range from really simple molecules, sort of like methane that we just looked at, through to absolutely massive ones like certain proteins. And when we're talking about really large compounds or molecules and macromolecules, obviously we're still talking they're very, very small. They're not the size of a building or anything, but they're made up of hundreds or thousands of individual atoms. And we're going to start investigating these over the coming lessons. And what we'll also see is that most of these organic compounds, along with carbon, also contain hydrogen and oxygen, and we'll see nitrogen crop up quite a lot as well. Okay, so what are we going to look at over the coming sessions then? Well, we're going to start looking at organic compounds, and what we'll see is that life is made up of 4 main classes of organic compounds. So everything that you see when you look at life, whether you're looking at a bacterium or an oak tree or a blue whale or us, we are made up of largely 4 main groups of organic compounds. And they are carbohydrates, lipids, proteins, and nucleic acids. So we're going to investigate these over the coming sessions. So the next lesson will be on carbohydrates. Following that, we'll look at lipids and nucleic acids. We might be able to do that in one session. And then we'll finish off by looking at proteins. And then from there, we'll look at enzymes, which are a type of protein. Okay, so that brings us to the end. So what we've looked at in this little section then are 2 different types of chemical bonds, ionic bonds and covalent bonds. And we've briefly discussed the 2 main types of covalent bonds, which are polar and non-polar covalent bonds. And we touched a little bit on what polarity is and why it's important to something like water. Okay, thank you very much.